All right, welcome everyone. Quick announcement, homework 4 is due at 5 o'clock today. Homework 5 is due a week from today. That's available now, and a lot of the questions deal with today's material, so you might want to give that a look after you finish homework 4. All right. So I am super excited today because we are starting hypothesis testing. So this is chapter 10, and this is where we finally get to start using statistics to use data to make decisions about answering research questions. So to get us into some of these concepts, we'll take this as our example. So our research question is, can dolphins communicate in an abstract way? And this is a study that was done in the 1960s. That's sort of one of the classic studies in animal psychology. So the deal was that the researcher, Dr. Jarvis Bastian, started out by training these two dolphins, Buzz and Doris, to press a button in order to get some food. So he trained them that when a light came on and stayed on, then they needed to press the right-hand button. And if the light came on and blinked, then they needed to press the left-hand button. So each of the dolphins learned how to do this individually. And then he wanted to test whether the dolphins could communicate with each other about which button they should push. So he set them up in a pool so that Doris was the only one who could see the light, and Buzz was the only one who could press the buttons. And if Buzz pressed the correct button based on the light that Doris saw, then they would both get fish. Right. And so the data were that Buzz pressed the correct button 15 out of 16 times. And our question is that convincing evidence that Buzz's long run proportion correct is greater than 50%? So is it convincing that he's doing better than just guessing? So here the 15 out of 16 is our statistic. That's our value that's summarizing what's in the data. And we could write this either as the statistic is 15 or the statistic is 15/16. Either way works. So we're trying to use the statistic to determine something about a claim about the parameter. So the parameter in the context of a statistical study is a numerical summary of the long run situation or about the whole population. So in this case, we're thinking about if Buzz pressed the button infinitely many times, what would his proportion correct be? Or what would his probability of pressing the correct button be? That's our parameter. Everybody got this idea of the setup? All right. So in order to investigate whether this is convincing evidence, the approach we're going to take is to suppose that we're in the world where Buzz is really just guessing, where his proportion correct is 0.5. So that's our chance model or our null hypothesis. And we're going to say, supposing we're in that world, how unusual would it be to get 15 out of 16 correct? Any ideas about how we might investigate this question of how unusual it would be to get 15 out of 16 correct if Buzz is just guessing? Niall?
What proportion is this?
Yeah, so we'll get there. Before we get to using a probability theory-based test, sort of a simple thing we could think about doing would be flipping coins, right? So we could let one coin flip be one guess by Buzz or one attempt at pressing a button. And we could say heads represents a correct guess, tails represents a wrong guess. And then one set of 16 coin flips would represent one instance of this study. So let's give this a try. So we're going to do this using the one proportion applet that is available on Canvas. So we're going to leave the probability of heads as 0.5 because that's our chance model that Buzz is just randomly guessing between the two buttons. We'll change it to 16 coin tosses. And so, for example, we could flip 16 coins and it'll flip them for us. And in this case, we got 8 heads and 8 tails. So we can graph that down here. This will be a dot plot with one dot at 8. So we had one study where we had 8 successes. Buzz pressed the correct button 8 times. All right, we can do that 99 more times. And so now we have this dot plot that shows the distribution of how common it is to get different possible numbers of heads when you flip 16 coins. Or in other words, the distribution of the number of guesses correct that Buzz would get if he really was just guessing. So can someone tell me what this graph is telling us about this claim about Buzz and Doris? Joey?
It's mostly normal.
This graph looks pretty normally distributed.
And 15 isn't even in the range that they're sitting there.
Yeah, that's the key part here for evaluating our claim about Buzz and Doris, is that 15 isn't even in this distribution. 15 is way out in the tail. So that means that if Buzz really were just guessing, it would be extremely unlikely for him to get as many as 15 out of 16 correct. So we say that this result is statistically significant. And so that means that we can rule out random chance. That is the idea that Buzz was just guessing and we just happened to get a lucky set of 16 here. We can rule that out as a possible reason for why he would have gotten 15 out of 16 correct. Because the chances of getting at least 15 correct are so small if the chance model were true. Questions so far? All right. Random chance is still possible, but it's not plausible. So it's not believable. It is still possible that random chance is what's going on. All we're saying here is that Buzz would have had to have been super lucky. All right. So that means that we've ruled out random chance as a plausible explanation. There are other plausible explanations. It might be that Doris and Buzz really are communicating. It might be that there's a pattern to the correct answers that Buzz has figured out. Like if the researcher had fallen into this pattern of like, okay, left button, right button, left button, right button. And so Buzz could have gotten into a way to figure out what the correct answer was going to be without having had to communicate with Doris. It might be that Buzz could secretly see the light around the curtain that was supposed to separate them. And maybe you can think of other possible explanations. So the idea here is that by doing this hypothesis test, we've ruled out random chance. But now the researcher may need to do additional studies to try to rule out all of these other plausible explanations. And he'd be aiming to end up with this first one. Sort of his goal is to demonstrate that dolphins really can communicate with each other. All right. What if Buzz had only gotten 12 answers correct? Then our result wouldn't be as extreme. It wouldn't be as far in the tail here. So what do you think? Would 12 out of 16 be a convincing evidence? Let's do thumbs up for yes, thumbs down for no. Just eyeball it. All right, so we got some thumbs down, some thumbs up, some thumbs sideways. It's harder to tell, right? So in order to quantify this, we use the p-value. So informally, the p-value is a quantitative measure of how far in the tail of, this is called the null distribution, our result is. So our null distribution is the distribution of values of a statistic that we would expect under the null model or the chance model. And formally speaking, the p-value is the probability of obtaining a value of the statistic at least as extreme or at least as convincing as the observed statistic that we got from our actual data when the chance or null model is true. So go ahead and get that into your notes, because this definition is going to come up a lot when talking about hypothesis testing. All right. So the smaller the p-value is, the more convincing evidence there is against the chance model. We often give the chance model the symbol H sub 0 that'll be our null hypothesis. So if the p-value is small enough, then we count this study as evidence against the null hypothesis. So an important question here is, what counts as small enough? Common thresholds are, will reject the null hypothesis if the p-value is less than or equal to alpha, where alpha is known as the significance level. And the most common choices for alpha are 0.05 and 0.01. So here, let's try this in the applet. We can ask the applet to tell us what the p-value is based on these simulations. So we can count the proportion of samples that are at least as extreme as 15 out of 16. So that was 0 out of 100, which gives us a p-value of approximately 0. So really the p-value is less than 1 out of 100. So that's saying that at a significance level of 0.01, we can reject the null hypothesis and say that there is enough evidence to claim the alternative hypothesis. So there is enough evidence to claim that Buzz's long run probability of pressing the correct button is greater than 0.5. Questions about this? All right, so let's give this a try, thinking about this simulation approach to understanding what's going on. So start by just reading that paragraph at the introduction so you can get a sense of what this study is about. And then try problems 1 and 2. And for folks who are looking at this online, this is the hypothesis testing hockey activity. All right. So for problem 1, we want to set up in symbols what the chance model is. So if there really is no difference among different months about how likely a professional hockey player is to be born in that month, then what would we expect for the value of P, the proportion of all NHL players who are born in January through March? So it would be 0.5 if we wanted to look at January through June, but here we just want January through March. So 0.25, yeah, first quarter of the year. If all the months are equally likely, then the first 3 out of 12 months are going to include a quarter of all the hockey players. Our null hypothesis is always going to set up a specific model that we can use to compute probabilities. So because of that, it's going to include either explicitly or implicitly an equal sign. So here we have an equal sign that's right there, it's explicit. In other cases, the equal sign might be implied, like if you write out the null hypothesis in words, it might be that the proportion of players in the NHL who are born in January through March is 0.25. So the word is standing in there for the equal sign. Small thing to be aware of is another way that you sometimes see this written is using the symbol pi to represent the unknown long-term proportion. So that comes up on a couple of the web work problems for homework 5. All right. Then for the alternative hypothesis, what forms of departure from the null hypothesis are we interested in investigating in this problem? Isaac?
There's more than 0.25.
Yeah, because we're interested in whether professional hockey players are more likely to have birthdays early in the year. So P or pi is greater than 0.25. Questions about this? All right, so with your groups, go ahead and do parts 3 and 4. So setting this up as a simulation-based problem.
There's one more. No. No, so it's number adult probability was 0.5. It wasn't. We're assuming that our null hypothesis is true. When we do these tests, we want to assume the null is true, and it's like this is all like the null is true, let's prove it. So we're just going to get this. Yes, let's assume the null hypothesis is true. Let's do this 1,000 times and see if we get various.
That's what I was thinking. Okay. No, I get it.
Yeah.
I thought, no,
Yeah.
that's probably, I was thinking that it's something else. So I was thinking this was actually other. But, yeah. At this point, not like that, exactly. Exactly that.
Right.
The other way.
Like it's greater than.
Yeah.
Okay, yeah, now we always are good about it, for sure. I'm sure that I don't know what that's what you need. I'm sure they have strong enough computers, right? Doesn't it? Like which kind? So what is that? No. Oh, shit. What's up? These are.
I don't know if I set it up right.
Yeah, 20 0.
Oh, yeah.
Oh,
You're wondering.
that would actually happen. I could have just seen this like there, but I'm sure you did it right. It's not very.
Yeah.
Just don't try. Trust your math.
Right. Yeah, if all the months really are equally likely, then it would be really unusual to have
Yes.
as many
I
as
mean,
63
that's
hours.
what
Roller nomination is different. It's different on
That's
that
why I
one.
did that.
So seeing 63 out of 101 players born in January to March is convincing evidence that the months it weren't all.
We'll get there. Or you can use the app and then we'll use it. So if you had access to it.
All right, so what should I fill in for the probability of heads? Kyle?
Is it 0.25?
It is 0.25 because we want to simulate according to the null model. So we want our probability of heads to match what we said in the null hypothesis. How many coins should we flip? 181, yeah, because that's our sample size. And how many repetitions do we want to use? 100 is good. 1,000 is good. Typically any relatively large, nice round number is good here. All right. So then the p-value is the probability of something. What is that something? Kyle?
The probability of actually getting the results that like the null hypothesis says.
So a result that is 63 heads?
Yeah.
Is it just 63 heads? Yeah, it's 63 or more heads. Oops. That's because the p-value is the probability of getting a value of the statistic at least as extreme as the observed statistic, not just the same amount of extremeness. So the reason why we do that is because let's imagine that we were flipping a coin and wanted to test whether it was a fair coin. I should stop sharing my screen. We want to test the null hypothesis that p equals 0.5. Probability of heads is 0.5 versus the alternative hypothesis that P does not equal 0.5? Let's imagine that you flip the coin 1,000 times and get 505 heads. If you got this, would you want to say that there was strong evidence against the null hypothesis? No, right? Because 505 is super close to half of 1,000. But the probability of exactly 505 heads is actually pretty small. You can do this using the binomial distribution. I think it works out to like 0.03. So if we were treating this probability of exactly 505 heads as the p-value, we would be rejecting the null hypothesis and saying, oh, looks like this coin isn't fair. But we don't want to do that because 505 heads is a pretty typical value to get. It's pretty close to the center of that null distribution if the coin really is fair. So instead, we want to use the probability that x is greater than or equal to 505 as our p-value. Actually, technically, for a two-sided alternative hypothesis, we'd use greater than or equal to 505 or less than or equal to 495. This ends up being a much bigger probability, like 0.63, somewhere around there. That is much more in agreement with our sense that we don't want to reject the null hypothesis in this case. That's why the p-value is the probability of obtaining a value of the statistic that's at least as extreme as what we observed, not just the probability of getting what we observed. Questions about that? All right. So then, using this idea that the p-value is the probability of getting a result that is 63 or more heads, what is our p-value from this graph? One 100th, yeah, because there's one dot that's out here that's, I'm not sure if that's at 63 or 64, but one dot that's out here that's at least as extreme as 63 out of 188. So go ahead and try writing our conclusion using a significance level of alpha equals 0.05.
Yeah.
Good. So if the question asked you in the context of the problem, think, to sort of summarize that, I'd say there is convincing evidence that players are not equally likely to be born. All right. So yeah, our p-value is less than alpha. So we're going to reject the null hypothesis. So if our question had asked us to write our conclusion in the context of the study, then we would want to say there is enough evidence to claim, and then fill in the blank with the alternative hypothesis. So there is enough evidence to claim that NHL players are more, yeah, let's do this, that the probability that an NHL player is born in January through March is greater than 1/4. Are there questions about this problem?
Would
Why
it
is
be
it?
fair to just say that follow our null hypothesis? Or like, we have to say it explicitly.
If the question says in the context of the study or something like that, then you do want to spell out like what was the alternative hypothesis
Sure.
about. All right. So now the question is, what if we don't have access to this applet? So what if you're doing this and you just have a calculator, perhaps? Well, our p-value is still going to be the probability of getting a result that's at least as extreme as what we got. So it's going to be the probability of getting, say, a number of heads that's at least 63. What probability distribution could we use to calculate this? Kyle? Yeah, we could use the binomial distribution. So X has a binomial distribution with, what's N? Kyle? Yeah, 181. Because we're flipping 181 coins, or we have a sample size of 181 people. And then what should our P, our probability of a yes result on any one person, or a heads result on any one coin? Sam? Yeah, 0.25, because we're still computing this probability, assuming that the null model is true. So go ahead and try using your calculator to compute this probability using a binomial distribution.
Well, I don't know what else.
So if we do like the one efficiency test, then this is like this one. Should be the same.
Not quite. Why not?
That's like, there's only this one versus that one.
Nope, because neither of them is random, so it's not like the applet.
Is it the one proxy is used by no CDF or use something else?
No, good question.
So it's not what we should do.
So the one prop Z test is actually using a normal approximation to the binomial. So I promised you back in chapter 7 that we would be using the fact that the normal distribution could be used as an approximation. Once we got to hypothesis testing, that's where it comes in.
So if we use normal CDF, like the 0.5 trick, it'll give us the same as the one proxy test.
That's a good question. I've never tested whether one prop Z test uses exactly what threshold one prop Z test means. Check it out right now.
So I looked up. Also, what if you can't approximate, like what if your sample size is large enough to be approximately normal?
Good question. So if your sample size is large enough to be approximately normal, then you would not want to use one prop Z test. Then you could use binomial CDF, or you could use the applet. All right. So to finish up with using the binomial distribution, what calculator function are we using? Sam.
Yeah.
Of what?
181. 0.5, and then 62.
Yeah, very good. Why do we use 62 here? Isaac?
Because if we want to know if it's greater than or equal to 63 for, we do it for random CDF, but if it's like less than a certain amount, then it'd be less than 62. Not including 63. If it included, then we'd be taking it out.
Exactly. So this is going to give us the probability that X is less than or equal to 62. Then we're going to take 1 minus that to get us the probability that X is greater than or equal to 63. And if you have trouble remembering which way the subtraction goes, the thing I always recommend is to draw a number line. Like, okay, how many people were born in January to March? Could be 0, up to 62, 63, 64, 181. So we're looking for the probability that the number born in January to March was in that region. So 63 up to 181. So if we're using the complement rule, then we're going to have 1 minus the probability of everything we didn't circle here. So 1 minus the probability of being less than or equal to 62. Questions about this? All right. So Niall and Joey and Kyle, you pointed something out about your calculators. What other calculator function did you use to compute this p-value? The one proportion z-test. And how did that compare with your answer to using the binomial distribution?
It was lower.
It was a little bit lower?
Yeah.
So the reason why that happens is because the one proportion z-test is not actually using the binomial distribution. It's using the normal approximation. So that's relying on this idea that when your sample size is large, like here we had a sample size of 16 or 181, what's happening here? Then our null distribution is going to be approximately a normal distribution. So that can be a quick and easy way of calculating the p-value. It's especially easier when you're using a two-sided alternative hypothesis. So if you're testing the alternative hypothesis that pi is not equal to 0.25 instead of that p is greater than 0.25, then one prop z-test is easier. But it does use a normal approximation. So if your sample size is small, such that a normal approximation to the binomial isn't a good fit, then you would want to use binom CDF, or you would want to use the applet. Questions about this? All right, so there are lots of other ways that we can test hypotheses depending on what type of parameter we're trying to investigate. So when our parameter was a long-term probability, we use the binomial distribution. And over the rest of this week and into next week, we'll see other ways of testing hypotheses using different models. I'll see you Wednesday.